Okay, guys, so we're ready to go over IS number 19, the hypothesis test formula study sheet. So notice it talks about 8-3 and 8-4. 8-2 is all about just an introduction to hypothesis tests. So these are the two sections that actually have specific processes for proportions and for means. So I just want to emphasize that 8-3 is talked about in the number 16 notes. So that's why I have those out here. Notice on that last page, the big ideas, it says section 8-3 above it. And then I also have the number 17 notes out here. If I flip those over, it says section 8-4, testing a claim or significance test for mu. Okay, so those are the two note sets that I'm going to be referencing, 16 and 17. So first of all, it says, what is the symbol for the statistic or from the sample? For significance test for proportions, this is the same as it was for confidence intervals. It's still p hat. The sample proportion is what we use to estimate the population proportion, which means our symbol for the parameter is p, okay, population proportion. Then the name of our procedure, well, I'm gonna come over and look at my 4-step process. Under the plan step, the name of the procedure now is a one sample, still one sample, z-test. It's C because we use the normal distribution for proportions, but this time it's a test instead of an interval for P, for the population proportion. So again, that is a one sample z-test for P. And then it asks how we check the conditions for this hypothesis test. So the random condition is the same. Once again, we check that we have a random sample. Okay, that's true for both proportions and means. 10% condition, again, is the same and must be less than 1/10 of the population size. Okay, true for means and, proportions and means. Now the normal condition is where things are different, or one of the places where things are different for proportions and means, but this is the same way that you check for intervals. So if I were to look back at my number 17, it's these exact same conditions. For proportions, it's large counts. For means, it's the 3 possible options. Notice we state that over here in the big ideas. We check large counts. Although this time it's a little bit different. It's not p hat like it was for intervals because we didn't know p. Now we'll have a hypothesis for what p is. And so we will use that to check. So again, we will use large counts here. And we will check n times p is greater than or equal to 5. And n times q is greater than or equal to 5. Remember, q will be 1 minus p. Okay, so before we start talking about the formulas, let's go ahead and, actually, I take that back. I'm going to go ahead and talk about proportions in their entirety and then compare them to the means. So let's go ahead and talk about the formula for the mean of the sampling distribution. That's stated right over here in our big ideas. Mean of the sampling distribution of sample proportions, or mu sub p hat, is equal to p, the hypothesized population proportion. So mu sub p hat is equal to p. So whenever I sketch my normal curve, the hypothesis for p will be in the center. The formula for the standard deviation of the sampling distribution, well, standard deviation is sigma, so sigma sub p hat is going to be, let's see, it was the square root of p times q divided by n. We had to use the standard error for intervals because we didn't know p, but now we have a hypothesis for p, so we use that. P times q divided by n, and then the square root of all of that. Okay, so we will again use these two as our parameters for the normal curve when we sketch it. Then we have a general formula for the test statistic. This is similar to our z-score, what we call it a test statistic now, because it refers to this hypothesis test. So that's that same test statistic. Test statistic is equal to the statistic minus the parameter divided by the standard deviation. And that goes for means and proportions, same thing. Notice we wrote that out in our do step, the general formula. We always write this out, okay? So let's fill in. The statistic here is going to be my p hat, statistic, The parameter here is going to be P, correlates to the mean for the sample proportions. And then my standard deviation, I'm going to fill in the square root. So the specific formula that I have, see how that works out. Z is equal to P hat minus P hat minus P divided by that standard deviation, square root of P hat times Q divided by N. P, sorry, not P hat. Okay, Z is equal to P hat minus P divided by the square root of P times Q divided by N. There we go. Remember, this is very similar to that z-score formula of value minus mean divided by the standard deviation. We just don't want to use straight up the word mean anymore, because when we get over to sample means, that'll be really confusing, right? Do we mean the sample mean or do we mean the population mean? So now we switch to statistic minus parameter divided by the standard deviation. Okay, so the picture, you have to draw the picture to get full credit, is going to be a normal curve. Ooh, that was not very good. Let me try that again. It's going to be a normal curve. I don't expect your pictures to be perfect, but I do expect you to try to make it look like that. We label it with an N for normal, and then we put the mean, which in this case is P, and the standard deviation, which in this case is that square root of P times Q divided by N. Now, of course, you're not going to write those exact letters. You're going to fill in what those values are, right? So every time we draw the picture, we have to calculate the standard deviation in order to label. P goes in the middle here, and then we add 1, 2, 3 standard deviations to it and subtract 3 to get our picture. Okay, finally, to find your p-value, we either use table A2, right? Use your z-score with table A2 and find the area that you're looking for, either a left area or right area. Remember, table A2 only gives left areas, so if you're looking for a right area, it should be 1 minus that left area. Or you can use the norm, I think it's normal CDF function from the calculator. Okay, 2 options there. All right, so let's just walk through the 4-step process real quick. You have to state the parameter, P equal to whatever in context, your statistic, the hypotheses, the null and the alternative, and then the significance level. So let's see what that looks like. You state your parameter, your sample proportion, your hypotheses, and the significance level. Okay. And then plan, you need to name the appropriate inference method and check your conditions. So that looks like naming the procedure, checking the conditions. Then you need to do, remember there are actually more than 4 parts now. For confidence intervals, it was just general and specific formulas, plugged in numbers are your work, and then your answer. But now you have kind of 2 different work things you need to show. The general and specific formula for the test statistic, plug in, and then state what that test statistic is. Then show your picture and your p-value. Your picture should match your p-value. So we have general formula, specific formula, work for the test statistic. Notice I show the test statistic work here and also finding that standard deviation that I could label my normal curve with and then be able to figure out the mean and then 3 standard deviations above and below. And then once I get my test statistic, I can use that to find my p-value. In this case, a test statistic, a z-score of 4.11, that's way higher than anything table A2 gives. So the left area was something bigger than 1.9999 actually. Since that's the left area, we subtract from 1 and we get something less than 0.0001. So essentially the p-value is 0. And notice when we go to try to label this sample proportion we had over here, 0.38 is way more than 1, 2, 3 standard deviations above the mean. It's about 4.11 standard deviations above the mean. And so we can tell there's almost nothing underneath the curve. That matches our p-value. Okay, so then our last step is to conclude. We make a conclusion about the hypotheses in the context of the problem. So I just want to remind you here that if your p-value is less than alpha, whatever alpha is, then you reject the null. Reject the null hypothesis. And of course, you have to put that in the context of the problem. So you'll say, we do have convincing evidence against the null, or meaning the same thing, you could say, we do have convincing evidence for the alternative. On the other hand, if your it's hard to write here at the very bottom of the page. If the p value is greater than alpha, then the opposite of rejecting the null is failing. Oh, sorry guys, my paper's a mess here. Then we fail to reject the null. We never accept the null. We only fail to reject the null if the p-value is greater than alpha. And in that case, we would say we do not have convincing evidence against the null or for the alternative. Okay, so that is for proportions. Now let's look at testing claims for means. So this is that section 8-4. So I'm gonna come over here to the notes I've got, and again, look at the IS number 17 notes, flipping over to the back and see my big ideas. So first of all, the statistic that I'm using will be the sample mean, x bar. And then the symbol for the parameter that I'm trying to estimate is mu, the population mean. The name of this procedure, see if I come over and look at my 4-step process, it's a one sample t-test for mu. So let's fill that in. This is a one sample t-test for mu. Notice the only two differences between the names for proportions and means. Obviously, it's for a proportion and for a mean. And then for proportions, we use the normal curve, so it's a z-test. For means, we use the t-distribution, so it's a t-test. Okay, so then we check our random and 10% conditions the same way as we do with proportions. The normal condition is where things get different, but this is, again, the same as for intervals. So there are those three options. Either your population distribution is normal, or n is greater than or equal to 30 so that the CLT applies, or the sample distribution shows no strong skew or outliers. Okay, one or the other of those. I'm sorry, one of those three is what you're looking for. Okay, so now when we're getting to the do section, we're going to need the formula for the mean of the sampling distribution. So this will be the mean for the sampling distribution of sample means, which is always equal to the parameter we're trying to estimate. So that's equal to mu. And then we will need the standard deviation. So sigma sub x bar. This was that sigma divided by the square root of n. But remember, if we're trying to test a claim about the mean, probably don't know the standard deviation. And so in that case, we will estimate it using the standard error of x bar, which is what we used for the intervals as well, s divided by the square root of n. Okay, we will use this one. Okay, and this is where it becomes a t-distribution. Because we don't actually know the population standard deviation, we have to estimate it with s. It introduces more variability into the distribution, so we have to have the t-distribution instead of the normal distribution. Looks very similar to a normal distribution, but it's a little bit wider at the ends. Okay, so our test statistic is the same. It's test statistic equals statistic minus the parameter, but we have a different statistic, parameter, and standard deviation. So the statistic is our x bar, the parameter is mu, and the standard deviation is s divided by the square root of n. So let's fill that in. And again, it's a t-test. We have to estimate the standard deviation, so we have t equals x bar minus mu divided by s divided by the square root of n. Okay, let's notice that we put that, or that we have that in our 4-step process over here. Our test statistic equals stat minus parameter divided by standard deviation is written right here. T equals x bar minus mu divided by s divided by the square root of n. And now we have to draw our picture. Again, it is a t-distribution. So let's sketch it. T-distribution. Oops. Okay. So again, it's supposed to have a little bit more area in the tails. I don't know that I actually drew it that way, sorry. The middle is going to be your hypothesized mu, and then you go up 1, 2, and 3, 1, 2, 3 down by the standard error. That's what you add and subtract. But I label it t and then whatever my degrees of freedom are. Okay, so finally, to find my p-value, I can either use table B and get a range, I would use degrees of freedom equal to n minus 1, or I can use TCDF. I would really prefer that you not use table B. I want you to get a precise value, so use TCDF. Okay, so the four-step process, again, works very similar for means as well. If you want another example, here is our four-step process on the back of the IS number 17 notes. I think what I do want to kind of walk through, I have my general and my specific formulas for the test statistic. I fill in those values. Remember, my sample mean minus my hypothesized mean divided by the sample standard deviation divided by the square root of n. I get 1.575. That means this sample mean value of 5.27 is 1.575 standard errors above the mean. I know it's above because this is positive. And if I look at my picture, 5.27 is about 157 standard errors above the mean. So since this sample mean is greater than the hypothesized mean, more extreme would be to the right, so I shade my curve to the right, and I'm trying to find this area. I know it's going to be kind of small, but I don't know how small it's going to be. So to find that, I could use table A3 again. I'd get that the p-value is between 0.05 and 0.1, but I really want to be specific, so I'm going to use TCDF, tell it my lower bound, so that's my left bound, of my test statistic 1.575. My upper bound is going to be some really big positive number, so 10,000 is fine. And then my degrees of freedom. Since sample size was 30, I subtract 1, I get 29. And that gives me my p-value of 0.063. Okay, again, my last step would be to conclude. In this case, our alpha was 0.05. Since 0.063 as my p-value is greater than alpha, we fail to reject the null, which again means we do not have convincing evidence that the true parameter in context is either, you can say the alternative, so that it is greater. I don't have convincing evidence of this, or I could say I don't have convincing evidence against the null. I don't have convincing evidence that the stream is not equal to 5. Okay, so that is the differences in our formulas for hypothesis tests for proportions and means. We're going to do the 8-2 and 8-3 test review in the next video.